All right, so we're going to continue our complex number talk. Okay. We are going to talk about powers and roots today, because those two go hand in hand. All right. So before we talk about what the shortcut is for powers, I want us to think about what it means to raise to a power. So like if I give you 4 to the 4th power, what does that really mean? Okay, 4 multiplied to itself 4 times, right? I guess you can take a different example. Like 4 cubed would be 4 multiplied 3 times, right? 4 times 4 times 4, okay? So powers are like repeated multiplication, right? Do we know how to multiply numbers in complex numbers in trig form? Talked about that yesterday, right? So we're going to use that to kind of help us make a discovery here. All right? So z is r cosine theta plus I sine theta. If we wanted to take z squared, that is just like taking z times z, correct? Okay. So if we take z times z, we multiply the r's. So r times r is r squared, do you agree? And then we add the thetas. What would our angle become when we take theta plus theta? Okay. There is z squared. Now, let's move to z cubed. Z cubed, we could say, is like z squared times z. Do you agree? Okay. So if we multiply these two numbers together, we have to take r times r squared. And then we have to add the angles. Theta and 2 theta would make. Okay. Z to the 4th. Z to the 4th would be like taking our z cubed that we just found and multiplying another z to it. If we were to do that, we would have r times r cubed for the r value. And then we would add our angles, theta and 3 theta. I'm going to give you about 30 seconds for you and your pod to discuss any observations that you have. Thank you. Okay, it seems awfully quiet in here. Let's see. Pi 4. Observations. Okay, so the power is telling you what power goes with the r and what multiple goes with the theta. This is what, help me out, Demois. Who takes French? Demois.
I'm just calling our good friend.
Okay, Demois figured out if we have a complex number, then the complex number raised to the nth power means all we have to do is take r to the nth power and multiply n to the theta. What's in red is Demois' theorem. Okay. Once again, if we are leaving a number in trig form, we still want it to be an angle between 0 and 360.
If on some occasion it ended up being like it was along, like it'd be 0 degrees or 360 degrees, which one would you have us use?
Either one would be fine. Okay. Now, I'm actually changing my example. I want to find radical 3 minus I raised to the 10th power. Let's talk about this. If we knew nothing about the trig form of complex numbers, what would we do? We would have to do 9 distributions. Does that sound enjoyable?
Yes.
No. Does that sound efficient? Okay. Let's not do that. Okay? What we can do is we can change this to trig form, use the Gauss theorem, and then change it back. Does that sound nice? Okay. So, let's first talk about radical 3 minus I. Find me the R value, please. Caroline, what's R? Do you agree? Square root of radical 3 squared plus 1 squared would be radical 4, which reduces down to 2. Now we have the tangent of theta equals negative 1 over radical 3. Is that a familiar ratio? Yes, yes it is. Okay, we need to know where the tangent of theta is. I'll even help you out. Negative radical 3 over 3. Which quadrant is this number plotted in? The fourth quadrant. So in the fourth quadrant, what angle has a tangent ratio of negative radical 3 over 3? What did you say? Negative 30, or we could say 330 degrees. Because I like between 0 and 360, right?
Yeah.
Okay, so now what we have is R cosine theta plus I sine theta. That is being raised to the 10th power. And if you want to use the shortcut, the shorthand, you can. Okay, the CIS. Right? So now, what we get to do is we get to take 2 to the 10th, and we get to multiply our angle by 10. All right, somebody with their calculator, what is 2 to the 10th? Now, I need you to subtract 360 from 3,300 until you get to a positive angle between 0 and 360. Be patient. You can use multiples. Have some people working ahead here. Already have the brain. What's our positive angle?
60 degrees.
60 degrees. That's nice, isn't it? You like 30 better?
33.
Oh, you like 3,300 better. Yeah. But now that it's 60 degrees, we can ditch the calculator. Right? Now, we started out with a number in standard form. What do I expect for your answer? A number in standard form. So, we can do that and we can keep it exact because we know the sine and cosine of 60 degrees, right? What is the cosine of 60 degrees? And we know that the sine of 60 is radical 3 over 2. So if we distribute this through, we get 512 plus 512 radical 3 I. And that would be our answer, even if we did the 9 distributions of that number to the 10th power originally. Can you imagine how many times we could make a mistake if we tried to FOIL that out? Yes.
What we could see is like calculators on tests.
Yes.
On the whole.
However, if I get a decimal right there, you're not getting full credit.
Oh, but I can check my answers. I'll do the work and I can check my answers.
Anytime, and this goes with vectors, this goes with these trig complex numbers. Anytime you have a special angle, I do expect exact answers. Okay? All right. So we can really see the benefit here of changing to a trig number because it did not take us very long to do that power, did it? No. Thank you, Dumois, for finding that out for us, right? Okay, before we go to lunch, we're going to talk about how to find roots. And then after lunch, we'll go through the examples of finding the roots. Okay? So first of all, what is a root? What's a root? Yes. Okay, that is true. Yes. So if I said, what is the third root of 8, what would you say? You would tell me 2, right? Because, why is 2 the third root of 8? Okay. All right, so 2 cubed is 8. All right. What you maybe haven't realized is that 8 has more than one third root. Any number, trig or standard form, because we can convert between the two, has exactly n nth roots. So any real number, excuse me, not real, I said that wrong. Any complex number has 2 square roots, 3 third roots, 4 fourth roots, 5 fifth roots. Okay? So if we're talking about the third roots of 8, yeah, we know 2 is a third root of 8, but there's also 2 other complex numbers that when you cube them, we get 8. Is that kind of mind-blowing?
Yes.
Okay? Now, how will we find them? Go ahead and write this down. Okay, so this looks slightly intimidating, but it's not. It's really plugging numbers in and figuring the rest out, okay? So if we are going to find the third roots, we plug in 0 to find 1, we plug in 1 to find a second, we plug in 2 to find a third, we're done. So that's a third root, right? If we're going to find fifth roots, we plug in 0, then we plug in 1, then we plug in 2, then 3, then 4, and then we'd be done. Okay? Basically, you start by plugging in k to 0, and then you stop until you have the number that you need. When we get back from lunch, we will go over it. All right. So as long as you have your number in trig form, you're going to take the nth root of the r, and then the theta will change with each root that you find. So whatever your angle is, you're going to put here. When k is 0, you won't add anything to your angle. When k is 1, you would add 2 pi to your angle, or 360, okay? For your next one, you plug in 2, so you take your angle and you add 4 pi, or 720 degrees, and divide by n, okay? It makes it so from 0 to 360 degrees, however many roots you have, they're going to be evenly spaced apart about that one rotation in the complex plane. Okay? So, it looks intimidating, but it is not. I will give this to you on the test. We just need to know how to use it. So our first example, we're going to find the square roots of this complex number right here. So what we're going to do is for our first square root, we're going to plug in k equals 0. Okay. So we're going to take the nth root of r, so the square root of 16, times the cosine. We're going to take the angle, which is 60. We are not going to add anything because k is 0. And then we'll divide by n. So what's our angle? 30 degrees. bless you. So what we have is 4 times the cosine of 30 degrees plus I times the sine of 30 degrees. So 2 radical 3 plus 2I is a square root of our original number. Yes. When we use this formula right here, so it's both for same, it's the same for both angles. We take our original angle, we add 2 pi times k, in this case k is 0, and then we have to divide by n. So we took 60 and divided it by 2 to get 30. Okay. What I did is I did the math here, and then I just simplified it for this angle. That way it would take up less room with my
Can
work.
we write the step where it's times 0 and then?
Sure can. All right, so now we need our second square root, which means we're going to plug in 1. So we have radical 16 times the cosine of, now, we have our angle, it says plus 2 pi k. Since we are in degrees, we're going to make it 360 k. What would our new angle become? What is 60 plus 360, then divided by 2? Okay? So we have 4 times the cosine of 210 plus I times the sine of 210. So our second square root is negative 2 radical 3 minus 2I. You will notice that since we're talking about square roots, our 2 square roots are 180 degrees apart. That does happen. Okay. If we were talking about 4th roots, they'd be all 90 degrees apart. Okay. But this is like the minimum amount of work I would want to see on your test or your homework or whatever it is. Okay. What questions do you have about using that formula? Dave.
How do you figure out how many?
They will always tell you what kind of roots you want. They want you to find, and that tells you how many. So if I ask you for 3rd roots, you would find 3 of them. 5th roots, you would find 5 of them. 4. 6th roots, you would find how many? 6. We're going to find the 6th roots of 1. Now, do we know any of them? What to the power of 6 equals 1? Do we know any of that? 1 to the 6th is 1. Negative 1 to the 6th power is 1. So we know 2 of them. They better appear in our work, right? But there's 4 additional complex 6th roots of 1 that we've never really even thought about before today. Okay? So, first of all, to apply that formula, what kind of form does our number need to be in? Trigonometric form. So, 1 is a nice number, but it needs to be in trig form. So, think about the number 1. What is its distance from 0? 1. What angle are we at? 0. So 1 is the same thing as 1 times the cosine of 0 plus I sine 0. Okay? This is the trig form that we will use. You ready? Let's do this. We will start with k equals 0. Remember, we want the 6th root of r, since we're finding 6th roots. And then for our angle, we're going to take the angle plus, in this case, 360 times k over 6, since n is 6. What's our angle? 0. So what I like to do to save room is I like to write the setup for the angle here, and then I'll do the math and rewrite the angle here so I don't have to take up 2 lines of work. Does that make sense? Okay? It's the same angle, but it's just saving me some room. All right? So we have the 6th root of 1, which is 1, times the cosine of 0 is 1, plus I times the sine of 0. Hey, 1 is a 6th root of 1. We already knew that. Let's find the next one. Now we're going to move on to k equals 1. So same process. We have the 6th root of r. But now our angle is going to be our original angle 0 plus 360 times 1 over 6. We take 0 plus 360 times 1 and divide that by 6. What angle do we get?
60 degrees.
60 degrees. So we have the 6th root of 1 is 1. The cosine of 60 is 1/2. The sine of 60 is radical 3 over 2. So when we distribute the 1 through, we get 1/2 plus radical 3 over 2i. If we take that number and raise it to the 6th power, we will get 1. Because it is a 6th root of 1. Isn't that cool? Okay. Okay. Let's move on to k equals 2. The 6th root of r. Now our angle is our original angle plus 360 times 2 divided by 6. Now what is our angle? What? 120. So we have 1 times the cosine of 120 is negative 1/2. The sine of 120 is positive radical 3 over 2. So our third 6th root is negative 1/2 plus radical 3 over 2i. Now, you will see some patterns in some of these root problems. I am fine with you using these patterns to a certain extent. Don't get too excited and start writing the answers. The patterns that I want you to look for are within the angles. Okay? How far apart have these angles been? They have been 60 degrees. As we find the next three roots, what's going to be true about those? They're still going to be 60 degrees apart, okay? All of these roots are evenly spaced throughout the one rotation on the complex plane. So if you figure out how far apart those roots are, you can use that pattern. So right away, for k equals 3, these have been 60 degrees apart. That pattern is going to continue. So we know our next angle is 180, I'm sorry. Okay. So we have 1 times the cosine of 180 is -1, and the sine of 180 is 0. So here we get the -1 that we were already talking about from the beginning. Yes.
Will the angles always be ones that will help in the circle, or will they be ones that will?
They will not always be unit circle values. If they are unit circle values, I want exact. But if they're not unit circle angles, then I want you to use your calculator, and that's fine. Okay. All right, so then for k equals 4, without having to use the formula, what would our next angle be? $240. Okay. We know the cosine of 240 is -1/2, and the sine of 240 is negative radical 3/2. And so our next sixth root is -1/2 minus radical 3/2i. Some of you are kind of getting an idea of what you think the next one is going to be. Okay. I think you're probably going to be right, but I still want to see the setup to how you get that. Okay. So since we're looking at the sixth roots, k equals 5 means we're on the last one because we started with 0. This is the sixth one that we are finding. If we keep with the pattern, our next angle would be plus another 60 degrees, so 300. So our last sixth root would be 1/2 minus radical 3/2i. Okay. Really, all you need that formula for is at least the first root, and then from there you can use patterns of symmetry. Okay? If you want to use the formula the whole time, you go for it, but it is okay after you find that first root to look at some symmetry with the angles. Okay? All right, we have a little bit of time left in class. What I'd like you to do is get out your gold sheet, get out your book, and I want you to go ahead and try the first problem. I want you to do one power problem before you leave.